Section 3.3, increasing and decreasing functions in the first derivative test. Remember, this chapter is a lot about analyzing graphs and using the derivatives to analyze the graphs analytically, not using the actual picture of the graph. Well, in the past, one of the most important uses of derivatives was to be able to sketch curves because they didn't have graphing calculators or computers to help them with it. Even though now we use calculators or computers to draw complicated graphs, it's still important to understand the relationships between derivatives and graphs. So if you have a function given to you as a picture, as the graph, and it says use the graph to estimate the open intervals on which the function is increasing or decreasing. Just looking at this graph, you can see all of this part is increasing. When it gets right to here, it's stopped increasing, but it hasn't started decreasing yet. So if this were a ball, it would be like hanging in midair, not going up, not going down. It's just ready to change direction. And then the ball would come back down. So this part of the graph is increasing. So for intervals that are increasing, we write these in interval notation, negative infinity, all the way up to what x value? Well, the y value is 4, but that x value there is 0. And then this part of the graph is decreasing. So our function has an interval from 0 to, so from 0 all the way to 2, it is decreasing. And notice I have open intervals because at the point 0 and 2, the function is not increasing or decreasing. Again, that ball is just frozen in midair. It hasn't started going up again or hasn't begun its descent yet. It's not going up anymore, not coming down, or not coming down anymore, not going up again yet. So we don't include the endpoints. And then increasing again, we can just use that same heading, increasing here, from 2 to infinity. So these are the intervals in which the function's increasing, and this is the interval in which the function's decreasing. What do you notice about the slope of all of the tangent lines on those intervals? So let's just analyze the increasing portion. What do you notice about those slopes? Positive, negative? Yeah, they all look like the derivatives are positive. Slopes of the tangent lines are positive. What about on this part? All these slopes are negative. And then again over here, for the graph that's increasing, the slopes are positive. So if we even didn't have the graph, if we just knew what sign the derivatives were, we would know what was going on with this graph. What sign's the derivative here, right at that top where that ball hasn't started descending yet, but it's done ascending? Hope you notice that the derivative there is 0, and this derivative here is 0. Notice we called those critical numbers when the derivative was equal to 0. Those are possible maximums or minimums. So the first derivative, if the derivative is positive, that means our curve is rising, our function is increasing. If the first derivative is negative, then our function is decreasing. And if the derivative is 0, it's a possible max or min. Remember, we could have a graph that goes like this, it has a horizontal tangent there, and then still increases. So it's increasing here, the derivative would equal 0, but it's not a max or a min, and then it keeps increasing after that. What's happening graphically at the place where the derivative changes from positive to negative or from negative to positive? I think we already discussed that. The derivative equals 0. What's happening graphically there means that the graph is changing from increasing to decreasing. So it has a possible max or a min. It has an actual max or a min because the derivative does change sign there. Here the derivative is not changing sign. The derivative here, all these derivatives are positive and all these derivatives are positive. So the derivative did not change sign here. But here, if the derivative does change sign from positive to negative, we have a max. And if our derivatives were negative here and then they change to positive here, right at that point where it changes, where the derivative equals 0, is our min. So then we can test the values of those critical numbers, all those places where the derivative equals 0 or where the derivative is undefined. We can test the derivatives on the sides of those points to figure out if the graph was increasing or decreasing, and that will tell us if that point is a maximum or a minimum. It's called the first derivative test. So if the sign of the derivative changes from negative to positive, so think about what that means. If the derivative's negative, your graph is decreasing. And then if your derivative changes to positive at C, what's going on at C? It's a relative minimum. Relative meaning it's lower than the points around it, but it may not be the lowest absolute point on the whole graph. If the derivative changes sign from positive to negative. So if derivatives are positive, the function's increasing, but then when it changes to negative, if the derivatives are negative, the function's decreasing. So at that value of c, we've got a maximum, a relative max. So it's the highest point compared to those around it, relative to those around it. If the derivative does not change sign, so if our derivative is negative, and then here the derivative equals 0, and then the derivative's negative again, then there's not a maximum or a minimum there. So the definition of something being a relative max or a min is that the derivative changes sign on the left side and the right side of it. An example, identify the open intervals analytically on which the function is increasing or decreasing. All right, I've got the graph here, but let's say we don't have the graph. What do? We want to know where the function's increasing or decreasing. So we take the derivative, 3x squared minus 6x plus 0. We set that equal to 0 because those will find us our critical numbers, the places where the graph could possibly change direction from increasing to decreasing or decreasing to increasing. When you set this equal to 0, you have to factor it and then set each factor equal to 0. All right, sorry. 3x equals 0 and x minus 2 equals 0. So dividing by 3 we get x equals 0, adding 2 we get x equals 2. So these are our critical numbers. So we could say c equals 0, c equals 2. These are the possible places where our graph could have maximums or minimums. But what we're looking for is where the graph is increasing or decreasing. So we set up intervals because at 0 and 2, those are the only places that this graph could possibly change direction, because that's the only place the derivative equals 0 or the derivative is undefined. Now this one does not have a place where the derivative is undefined because there's no denominator. So if we set up intervals from negative infinity to 0, and then between 0 and 2, and then after 2. So if you've got two critical numbers, you're going to have 3 intervals. So if you want to think about your number line, if that helps you, if you'd prefer to do a number line, we've got this region, and this region. So negative infinity to 0, 0 to 2, and 2 to infinity. So if you prefer a number line, you can do that instead of setting up intervals. But what we want to do is figure out what the derivative is doing between negative infinity and 0. So if we pick a number and plug it into our derivative, we'll be able to find the sign of the derivative. So pick a number in this interval, any number less than 0, like negative 1. So if we take negative 1 and we put it in our derivative, negative 1 squared is 1. 3 times 1 is 1. Minus 6 times negative 1, so that's going to be plus 6. So that's 7. I don't really care about the exact value. I just care if it's positive or negative. And so it's positive because it's a positive 7. How about a number between 0 and 2? Oh, if you prefer a number line, you can just write a positive above there. Between 0 and 2, pick a number like 1. All right, so we're going to pick a number like 1. Remember to put it in the derivative because what we're trying to do is figure out what the sign of the derivative is, because that tells us what if the graph is increasing or decreasing. And we know every value between 0 and 2 is going to have the same derivative because these are the only two places where the derivative could possibly change sign. So at 1, we've got 3 minus 6, which is negative. So our derivative's negative there. And then after 2, any number after 2, like 3. So you could have 3. 9 times 3 is 27, minus 18. Again, that's positive. We don't care what the actual number is, just if it's positive or negative. So if you're using a number line, use that. Now, what does it mean if the derivative is positive in a certain interval? It means that the graph, the function, now don't use the word it. You know, it is positive. What are you talking about? The derivative being positive or the function being positive? It is positive, don't say that. Say the derivative is positive, so that means the function is increasing. The derivative here is negative, so the function is decreasing. The derivative here is positive, so the function here is increasing. All right, use the notation. Don't be sloppy. Don't use the word it when you're using a sentence, because on the AP test you have to write out exactly what's going on. Here, f is increasing, decreasing, increasing, I'm just saying f here once to show all these things, and you could say derivative here is this positive, negative, positive. So be sure about what you're saying is positive or negative, or what's increasing or decreasing. So that's the increasing and decreasing test. And if you look at the graph, now that we've analyzed it without using the graph, let's see if it matches. Up to 0, the graph is increasing. Between 0 and 2, the graph's decreasing. And after 2, the graph's increasing. Yes, it is. On the AP test, it is not sufficient to draw the chart, like the number line. You can't just write this, and then you can't do that. That's not good enough. You have to have a written answer, like there's a local maximum, or the function is increasing at, increasing at, or increasing between 0 and 4, or increasing or decreasing between. You have to say complete sentences. So let's do an example here. Find the critical numbers of f, if there are any, the open intervals on which the function is increasing or decreasing, then apply the first derivative test to identify the extrema, and then graph it. All right, I graphed it first, just because it's easier for me to put it in right now. So let's take the derivative, 1/2 minus cosine of x. Set the derivative equal to 0. We're trying to find critical numbers, okay? So you can add cosine of x to one side. Think about your unit circle. Where does cosine equal 1/2? We know it's in a 30, 60, 90 triangle. Cosine is the x value, and 1/2 is shorter than the square root of 3/2. So we know that cosine is short on this side, long on this side. That's our triangle. That's going to be the 60-degree angle, or pi over 3. So x equals pi over 3. Where else is the cosine equal to positive 1/2? Over here? Nope, that's a negative cosine. Over here? Nope, again, negative cosine. But here, yes, positive cosine, negative sine, that's okay. We still have a positive cosine equals positive 1/2. So what's that value? 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. Get used to doing this without your calculator. Every time you have a chance to work on a major angle, practice it. Don't just say, I'll learn it before the AP test. Practice it every time. The open intervals in which the function is increasing or decreasing. Usually they would give you, if you're using a trig function, an interval. Let's say we're just going from 0 to 2 pi. They'll give you the interval on which x is in, so that you don't have to list every answer to infinity. So remember, when we find a critical number, these are the only two places where a function could possibly change sign. The derivative could possibly change sign. The only two places where we could possibly have a max or a min. So from 0 to pi over 3, I'm using 0 and not negative infinity because my interval starts at 0. Pi over 3 to 5 pi over 3, and 5 pi over 3 to 2 pi. So think about a number between here and here, and we're going to test it. So like pi over 4, we're going to test it in the derivative. So 1/2 minus cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. What's 1/2 minus square root of 2 over 2? All I care about is if it's positive or negative. So you should know that square root of 2 is about 1.14. It's a little bit bigger than 1, right? Because the square root of 1 would be 1. The square root of 2 has got to be a little bit bigger. So if you do 1 minus that, it's going to make a negative number. Some number between pi over 3 and 5 pi over 3. We can pick any number from here to here. See any easy ones? Yeah, let's use pi. So 1/2 minus cosine of pi. What's the cosine right here? Negative 1. So we have 1/2 minus 1, negative. So that means our function, since our derivative is negative, our function was decreasing here and decreasing here too. So what's pi over 3? Nada. It's nothing. It's not a max or a min. And then here, pick a number between 5 pi over 3 and 2 pi over 3, like 5 pi over 6. Wait, is that right? 11 pi over 6, sorry. 11 pi over 6.